Hi there, welcome back to the channel. Let's solve an example on the proof that we did yesterday on distribution of charges. Okay, so if you have not seen that video, you may not understand this, so do well to subscribe to first subscribe to the channel and go and see that video. It will be linked in the description below. Please see that video in order to understand what I'm doing here or what I will do here. Now, a thin non-conducting rod of finite length L carries a total charge Q spread uniformly along it. Okay, so we have spread our charge Q, infinitesimally small charges over that length of the wire. Is that clear? And the wire is very thin, and it has a consistent or a constant charge density. Now show that the field at a point P on the perpendicular bisector at a distance y is given by this equation. All right, so let's put that in diagram so that we can understand what is happening there. So we have a long non-conducting wire and it has a finite length. Now our wire is thinner than this, but so that for visibility, that is why I am making it as thick as this. Our wire is very thin and the charges are distributed over it uniformly. We're using positive charges now. It has a length, a definite length. A definite length L, okay? It now says that, so the charge is Q, the sum of the charge is Q, spread uniformly along it. Show that field at a point P on the perpendicular bisector. On the perpendicular bisector, what is the perpendicular bisector? Let's draw a perpendicular bisector. This line is the perpendicular bisector. So at a point P on this perpendicular bisector, so this is point P, that the field is given by this, and this perpendicular bisector is at a distance y, or this point P is at a distance y away from this charge. Okay, if we introduce our triangular, make it into a triangle, we're going to have this. So that from here to here, which is, since it is bisected, if it's bisected, it means it's split into half, right? So it means that from here to here will be half of this length. So and half of the length is going to be L over 2. I hope that makes sense. Okay. If that be the case, then this place, first this will be our angle theta. Okay. So now we know this. So what will this place be? This place, let's call it R. Okay, no. We can get this place is our hypotenuse, that is right. So, and that place becomes, let's say R is going to be equal to this squared plus this squared. So R squared equal to L over 2 squared plus Y squared. So that our R becomes the square root of Y squared plus 1 over 2 squared. So, no, L over 2 rather. L over 2 all squared. So that's what this place will be. Root y squared plus L over 2 all squared. Okay, so we have this. Now, remember or recall from when we're trying to prove the equation yesterday, I'm going to pick one part of that equation since I already know it. So I'm going to pick it. If you don't understand what I picked, just go back and watch that video. I would advise that you see that video first. So that part says that E sub dy, dEy rather, will be equal to, the integral of Ey is going to be, the integral of dEy is going to be lambda over 4 pi epsilon naught y integral of cos theta d theta. If you remember, we had this. So by the time you take the integral of cos x, and that was the integral of E dy, okay, there was a part where we had this, so I just bring that part into this concept. Okay, so by introducing this, when we take the integral, we're going to have e sub y. Remember that yesterday we said the sum of the electric field is going to be just the one due to the y-axis, because the one due to the x-axis will cancel out on either side. Is that clear? Okay. And of course, here it will also be the same, because there is also symmetry, because the point we are picking is at the center of the distributed charges. Okay. So this becomes lambda over 4 pi epsilon naught y. Integral of cos theta is going to be, let's take an indefinite integral. Integral of cos theta is going to be sine theta. Okay, so in that case, by the time you solve the thing, you do your integration and all, you remember it's a standard integral for what I did. This value here is going to become 2, because 2 is going to add to this guy, and then just make sure you see that video so that you understand what I did, so that our e sub y becomes, and it is so even when we are integrating between theta and 0. Does that make sense? Okay, so that it becomes lambda over 2 pi epsilon naught y sine theta. Okay, so if this is the case, then we know that sine theta is opposite over hypotenuse. Opposite over hypotenuse. And what is the opposite? The opposite is the one facing this angle, which is L over 2. L over 2 over hypotenuse is going to be that side, which is square root of y squared plus L over 2 all squared. Okay, so it means that our sine of theta will be equal to, let's simplify that, L over 2 over square root of y squared plus L squared over 4. Okay, that means that it becomes L over 2 all over the square root of, let's take the LCM, so we have 4 over, we're going to have over 4, this one will be over 1, so 4 in 1, then we have 4y squared plus L squared. I hope this is clear. Okay, so if that be the case, then we can have our sine theta to be equal to L over 2 over 4y squared plus L squared over 4 all raised to the power half. Okay, so if this be the case, then we know that we can take the square root of this guy, right? We can take the square root of this guy, and we'll have L over 2 over 4y squared plus L squared, opposite, yes, over hypotenuse. Okay, all raised to the power half over the square root of 4. Okay, I return the square root to this denominator. Okay, so that this becomes L over 2 divided by 2 over, multiplied by 2 over 4y squared plus L squared all raised to the power half. Okay, so this takes care of this. So we are now left with our sine theta has now become L over 4y squared plus L squared all raised to the power half. It's looking like it, right? Or square root of that. Now this is going to be L. No, okay, it's 1. Okay. So by the time we introduce this into our equation, we're going to have this. Recall that E sub y is equal to lambda over 2 pi epsilon naught y, 2 pi epsilon naught y, dot this, dot L over, which is sine theta now. We substitute this guy for sine theta. Substitute for sine theta. Okay, so that will be, now one mistake, or it's not a mistake, one thing I am not doing that you're supposed to do is actually to label your equations. But I'm trying to quickly solve it, that's why. You should label your equations so that your examiner, will, in case you are told to prove things like this, you label your equation. So you substitute for sine theta, so L over 4, so square root of 4y squared plus L squared, okay? It's not looking like it yet, okay? There's Q. Recall also that charge density lambda is Q per L. Because remember, we did only a small segment yesterday, which was dq dx. But it's over the entire length, so it's going to be Q over the entire length, Q over L. That's charge density, okay? So we replace it into the equation. We need to replace charge density. So we have Q over L multiplied by 2, multiplied by, this thing is going to be Q over L, yeah? Multiplied by 1 over 2 pi epsilon naught y dot L over 4 pi and 4y squared plus L squared, square root of that. Okay, yes. So it's now looking like it. So L is going to take care of L, and E sub y will be equal to Q over 2 pi epsilon naught y dot 1 over square root of L squared. So we can just L squared plus 4y squared. All right, so that is it. Do well to subscribe to the channel. In the next video, we are going to treat distribution of charges over a surface and over in a ring at an axial point in a ring. Is that clear? Those are the two that we're going to do next. Share the video and subscribe to the channel.